Alright, thanks for watching and welcome to my 100th video special. I can't believe it's already happening. It's crazy. But, I was thinking, what should I do for my 100th video special? And it should really be special. So, a bunch of people asked me, what did I do for my PhD research? Or how does one get a PhD in math? And I thought it would just be perfect if in this video I talked about the research I've done as a grad student. And so, as you may know, my field is in the world of partial differential equations, which are equations which model real-life phenomena. And in particular, what I did in grad school is I studied a PDE which models a chemical reaction. However, just disclaimer, I do not know any chemistry. The only chemistry I've learned is from Breaking Bad. So, which means in math you don't need to know, your applied field if you want to do math, because you're just focusing on the math. Alright, and so let me start with the great debate of chemistry. And please, if you know chemistry, don't laugh at me. As I said, I don't really know much about the background. But apparently it's a great debate. So let's consider the following simple chemical reaction. A goes to B and vice versa, where a molecule A becomes a molecule B and a molecule B can transform back into a molecule A. Think, for example, as a protein that unfolds and then folds back. So in this case, we only have two states. And then it turns out there are two ways of viewing this chemical reaction. On the one hand, there is a macroscopic level. I think it's a high energy level or something. Level. On the one hand, you can say, hey, there are only two states, A and B. Right? So there are two states. A, which you can model by a concentration, so let alpha T be the concentration of A at time T, and beta, similar for B, beta T is a concentration of B at time T. And of course, you can assume that alpha plus beta is equal to a constant, thereby eliminating the necessity for beta, but let's just keep it dual. It's nice to keep those two variables. Then, it turns out, using chemical modeling, alpha and beta have to satisfy a certain ODE called the reaction-diffusion system. Namely, under some chemical assumptions, we in fact find that alpha and beta evolve according to the ODE. Alpha T is kappa beta minus alpha, and beta T is kappa alpha minus beta. Where, again, alpha T, it's the time derivative and of alpha, beta T is a time derivative of beta, and then kappa, it's what's called a reaction rate constant, and it turns out apparently in chemistry it's a big deal to have this constant and to calculate exactly how fast your reaction evolves. And let's think about this a little bit intuitively. What does that say? So suppose you have some region, let's say, where there are lots of A's and just a little bit of B. So suppose you have this region, a lot of A's and then just a little bit of B. What does that mean? It means that, in fact, alpha is much bigger than beta. And therefore, beta minus alpha is less than 0. However, if beta minus alpha is less than 0, it means that alpha T is kappa beta minus alpha. This is negative, This is just a positive constant, which tells us in the end that alpha t is negative. And therefore, what this tells us is, in fact, alpha is decreasing with time. So, if you have a situation where there's a lot of molecules A, by this law, we know that the concentration of A decreases, and you get maybe something where you get less A, and by duality, you get that there is more B. And it turns out, after a while, there is some equilibrium where in the end you get roughly the same amount of A and B. Because if there are more B than A, by the second equation you find that B is, will be decreasing, and then we do get an equilibrium. Which means that this equation, at least in applications, does make sense. It tells us that in a chemical reaction, we eventually attain equilibrium. Okay, but this is not why we're here today. Here we want to discuss another aspect. But before I move on, you might say, hey Peyam, you've been lying to us. Because, as I said, I study PDEs, but this is just an ODE. And you may say, what went wrong? Well, first of all, stick around. I will talk about PDEs. But also, to streamline this talk, I assume that alpha and beta are just functions of t, but you can generalize this a little bit by adding the fact that alpha and beta could also depend on the space x, and then if you add this x dependence, you actually get that alpha and beta satisfy a bunch of heat equations. So just note, more generally, we have the following, that alpha t minus the Laplacian of alpha is kappa of beta minus alpha, and beta t minus Laplacian of beta is kappa alpha minus beta. Where here alpha and beta, they're functions of x and t, and beta x and t, and the Laplacian is just the sum of the xi derivatives, the same xi derivatives. Okay. And so, in fact, the full model is a PDE, and it's in fact analogous to here, but again, just to streamline the presentation, we forget about the x dependence and just talk about the t dependence. And by the way, this thing here, it's called a diffusion operator or heat operator, and that's why this equation is really called a reaction-diffusion equation, because the right-hand side is a reaction part, the left-hand side is the diffusion part. Okay, so that was the macroscopic level, where we just have two states. On the other hand, let's see what happens when we zoom in. So what happens on the microscopic level? Then you'll see something interesting is happening. So on the microscopic level, we have the following. On the microscopic level, think of the following. Instead of having just two states, A and B, imagine you have infinitely many states where the left-hand side would be A and the right-hand side would be B. In other words, there are infinitely many states which you can parameterize with what's called a chemical variable xi, where xi of -1 is A and xi of 1 is B. And I think the analogy with proteins is very nice, because if you think of a protein unfolding, folding and unfolding, you can think of one state as being A, but then when you're folding it, you do have infinitely many states, and each state you can parameterize by xi until you get the other state, B, which is parameterized by xi equals to 1. Okay? And what's nice about this is that once we have this extra variable, we can give a little bit more probabilistic interpretation of a chemical reaction. Namely, instead of thinking of a chemical reaction as just having A and B, imagine that you have a molecule that bounces back between A and B with the following law. Namely, imagine of a molecule bouncing back and forth on what's called a double well potential function, which is a weird function that gives you the energy of a molecule at a certain position. So, and usually in this case, the double well potential function looks like that. You have xi and you have h of xi. Xi and h of xi. It's just a function that depends on the chemical variable xi, and each well here is each of the states A and B. So here again, xi equals to -1 would correspond to A, and xi equals to 1 would correspond to B. So lots of anxiety involved. Get it? And as I said, think of the molecule as just a marble that bounces back and forth between A and B. Like this, it goes like this, woo, 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 and then here, once it reaches here, it bounces back to A, etc., etc. And then whenever the molecule goes from A to B, that's precisely when a chemical reaction occurs. And the nice thing is, it sort of shows also how, a reaction can be reversible, because going back from B to A, the marble just follows this potential. But mathematically, we have that also the function is even, has two local minima at this point and this point, and blows up to infinity here, so that there's not another state where the molecule can be. Okay, and let's introduce a little bit more math. So on this potential, probabilistically, the chemical reaction is random. So this marble performs a Brownian motion, and in particular, using this Brownian motion, we can model it by what's called the stochastic differential equation, which is a random differential equation. And from this stochastic differential equation, we can extract what's called a Fokker-Planck equation. And from this equation, we can extract another equation, which we'll study now. It's what's called the kramers-smoluchowski equation, which is given as follows. So again, using a bit of probability, we get the following equation. Sigma ut equals to sigma over tau u xi. And what's called the Kramers-Smoluchowski equation. So we get this equation, which is supposed to model the chemical reaction at the microscopic level. And you may say, what the hell is this gibberish? Let me explain all the terms, which maybe it makes more sense in a second. So where? Okay. On the one hand, u, it's a function of two variables, xi and t. So it's a function of time and this chemical position, but it turns out there's also an epsilon dependence, which I'll talk in a second about, and that's just the density of the particle. And strictly speaking, it's the probability density function of the particle. Sort of like how the Gaussian distribution has this e to the minus x squared. Or think of the distribution of this chemical reaction being given by U epsilon. And then, what in the world is epsilon? Epsilon is what's called the zooming factor. And think of epsilon equals to 0 as the macroscopic state. And anything positive is the microscopic state. Oh, and then epsilon positive micro. And sigma, it's basically H except scaled by a certain constant. So sigma is sigma epsilon of xi, and it's just equal to some constant e to the minus h of xi over epsilon squared. Again, if you ignore this epsilon, it's more or less h, except you exponentiate it. And this epsilon squared factor, what it does, it makes the well being infinitely high. Something like this. Okay, so this is h over epsilon squared. And the interpretation of this is, it makes it much, much harder to go from A to B. And this is why when you see in nature, you don't really have a chemical reaction every second. Sometimes it takes years, for a molecule to transform to another one, and the interpretation is that epsilon is usually very small to make the passage from A to B very, very hard. So sometimes it takes years to go from A to B. And C epsilon, think of this as a certain constant, again, not too important, but C epsilon is chosen such that just the integral of sigma is 1. So that the mass doesn't escape to infinity or something. We want a uniform mass. And so that explains our U, explains our sigma. Tau is again another scaling factor that makes this work, because it turns out if tau is too small, we just get 0. If tau is too big, we get instantaneous equilibrium. And there's precisely one factor which makes this wonderful. So E of 1 over epsilon, e to the minus 1 over epsilon. It's an equation, it's a constant which gives us a nice equation in the end. So sometimes in math you do wishful thinking where even though this might not appear in nature, it's the equation that makes it mathematically interesting. Okay? And yes, it looks like a mysterious equation, but by the way, this is a PDE because u xi, that just means differentiate u with respect to xi, and also differentiate this whole thing with respect to xi. So we have xi derivatives here, and we have a t derivative here. And yes, it is a very mysterious equation. However, if you think about this a little bit, if you ignore the sigma and the taus, then this actually becomes ut equal to u xi xi, which in one dimension is just a heat equation. So this is just a modified heat equation. Okay? All right. So now I have discussed two models. I have the macroscopic model, where you have simple system of ODEs, and you have the microscopic model, where you have this very strange PDE, this weird heat equation. And this is, again, applied math is sort of like that. First part you explain the background, and now you actually do the math. Now, the thing is, as I mentioned, this depends on epsilon. This depends on the zooming factor. Well, the question is, what happens to this equation as epsilon goes to 0. And magically, if you let epsilon go to 0 here, you get the first equation. Whoa! Let me clarify. So let me talk about the main result. Because you might say, how in the world are those two equations related? We have first of all, the first equation is a 1D equation, just depending on time. Here we have a 2D equation, depending on xi and t. How can a 2D equation transform into a 1D equation? That's one thing. Also, we have two different variables. Here we have u, which depends on xi and t, and we have alpha and beta, which just depend on t. Well, the thing that saves us here is, drumroll, linear algebra. More precisely, functional analysis, which is infinite dimensional linear algebra. More precisely, the thing that saves us here, it's a certain kind of convergence that's very well suited when we have two different objects. It's what's called a weak star convergence. So here's a main theorem. Namely, take your function u of xi t. Strictly speaking, u doesn't go to what we want, but if you scale it with this factor sigma, so if you multiply it with the factor sigma, then it does go to something interesting. It goes precisely to the functions we have before. It goes to alpha t, and we have to add a little Dirac function. Dirac of xi equals to -1, plus the same thing with beta, plus beta t Dirac of xi equals to 1. In other words, Dirac delta at -1 and Dirac delta at 1, except just at the point psi. And I like to remind you that Dirac delta distribution, okay, not function, it's a distribution that it's 0 everywhere, but it spikes up at x, and here it's infinity. So that the integral equals to 1. So, in other words, if we ignore this term, what it says is, if you take u and you scale it with sigma, it does go more or less to alpha and beta. And I'll explain in a second why this makes sense, but let me quickly explain this weak star convergence. Weak star convergence, in this case, means the following, in the sense that for every phi, for every Tesca function, continuous, phi that depends on xi and t, and for all time, think of terminal time, greater than or equal to 0, we want something that patches those two things together. It turns out with integration we can do that. If you take, again, sigma u, so the left-hand side, and multiply this by phi, and you integrate this from r, and I guess from -infinity to infinity, and from 0 to t, so d xi dt. Nice thing is, you get a fixed number, okay? And numbers are sort of what puts everything together. This is a fixed thing. It depends on epsilon. But if you let epsilon goes to 0, we want this to be equal to this thing. But what happens is you still have your alpha t. But then you have a phi of xi t. But what this Dirac delta distribution does, it concentrates phi at -1. So you end up with phi of -1t alpha t plus same thing with beta, phi of 1t beta t, and you integrate to get a number from 0 to t. So once you do this business, you actually find that you have a number that converges to another number. And real convergence is the thing we can deal with. And this is really the thing that patches those two weird worlds together. This is the passage from the microscopic world to the macroscopic world. And by the way, you may notice this is a bit similar to what I did in the video about distributions. In fact, phi is a kind of a test function. We're telling if you, for every test function, if you multiply and integrate, it converges to the thing where you multiply the right-hand side by the test function and you integrate. Okay, and what does that mean in terms of, intuitively? Intuitively, it means the following. It means that for t fixed, if you consider the sigma u, it goes to two spikes, one with height alpha and the other one with height beta. So for small epsilon, sigma u looks something like that. You have one spike here and the other spike here. -1 and 1, and this is psi. And the heights of the peaks are alpha t and beta t. And this sort of explains also, because the passage from macroscopic to microscopic. Because in the macroscopic sense, you have like a string, that, with infinitely many states. But what it says is, if you take the limit in the macroscopic state, the string breaks, and you just have two endpoints, one with height alpha t, and the other one with height beta t. And also, strictly speaking, it should make sense because sigma, remember, it looks like e to the minus h over epsilon squared or something. E to the minus h of xi over epsilon squared. And so, as long as h is positive, it should go to 0. And more precisely, when h is 0, it just concentrates there. So, in other words, it concentrates at whatever h is at h of -1 and h of 1, which also explains this concentration phenomena at -1 and 1. Okay, lots of intuition. And by the way, the proof of this is pretty standard in PDE theory. You just prove some basic estimates that show that, sigma u, square root of sigma u is bounded in L2, if you know what that means. And then using some basic functional analysis theorems, you find that you have this weak star convergence. Because the nice thing about weak star convergence is, even though it's very weird, a lot of things weak star converge. You just have to show it's bounded, basically, in some space. And it's the analogy with like a bounded sequence in real numbers as a convergent subsequence, more or less. Okay. But again, this is not why we're here today. It's not to show that this converges. What's more interesting is we want to figure out what PDE the alpha and beta satisfy. And more precisely, we want to show that alpha and beta, in fact, satisfy the PDE, the reaction-diffusion system from the beginning. So, we know, again, by the main result now that our U converges to alpha and beta, and then now the more important result is show that alpha and beta solve the reaction-diffusion equation with a certain kind of constant, kappa is square root of h double prime of 0, h double prime of 1 over 2 pi. And the thing is, h double prime, well, at 1, because we have a local minimum, h double prime is positive, so that's why we don't have absolute values. But here at 0, h double prime is negative, and so we need the absolute values. And by symmetry, I forgot to say those two are this. You assume that h double prime of 1 is h double prime of minus 1. Okay, so again, where are we at? We've shown that sigma u converges, to alpha and beta, but again, we do not know yet that alpha and beta solve the reaction-diffusion system, but now we will show this. And more importantly, we have this factor of kappa, and again, it's apparently a big deal in the chemical world to determine this constant kappa, but what it says is this constant is determined in terms of h, which again gives us a analogy between the chemical reaction rate and the probability potential function. Okay, and this thing is so cool, let me actually prove that. So here's the idea of the proof. And I promise I'll keep it on the down low, so it's not, I won't do something crazy difficult. The idea of proof. Because it turns out, even a calculus student can do this. And again, not in a condescending way, it's because it doesn't use more than an integration by parts. Because, let's start with the following. Start with sigma ut is sigma over tau u xi xi. Right? Our original kramers-smoluchowski equation. And the thing is, this term, and trust me with that, this term is bad. It's bad, okay? Because what happens, this term basically blows up at -1 and 1, and we would really like to get rid of it. And if you want to get rid of it, let's just kill it, and we'll kill it with an integration by parts. So the idea is, we'll take this equation, we'll multiply it by a very clever function and integrate by parts. So let phi be the following. Phi of xi depends on epsilon, but the point is it doesn't depend on time. It equals to the integral from 0 to xi of tau over sigma d xi. I guess d xi prime, anyway. In other words, what this is just an antiderivative of tau over sigma. Okay, and that's good because we want to differentiate this. So let's do that. And by the way, I am hand-waving this a little bit. Strictly speaking, you want to multiply this by an arbitrary test function. You want to cut this off after a long time so that this does make sense. But let's ignore, those technicalities. Take this star, take star, and multiply star by phi and integrate over -3/2. And the reason is all the terms are well behaved at -3/2, so we get the following: -3/2 sigma ut phi d xi equals to integral of -3/2 sigma over tau u xi phi d xi. And let's analyze those two terms. So we love to integrate in PDEs because hopefully with integration some of the derivatives disappear. Okay, now let's study this term a little bit and recall from 1. So for 1, recall that we had that sigma u, it sort of converges to alpha Dirac at -1 plus beta Dirac at 1. Turns out, that's the nice thing, we can also differentiate this with respect to t. So sigma u t, it goes to alpha t Dirac at -1 plus beta t Dirac at 1. And remember, sigma doesn't depend on t, so that's really sigma ut. And again, I am being a bit hand-wavy here, so you can definitely make this rigorous, and you can check out my thesis to see how to make this rigorous. Okay, so that's good. We find that sigma ut, this term, it basically concentrates at minus and 1 with this alpha t term. So what this says, so by definition of weak star convergence, because you're multiplying it by phi, we get that 1 goes to alpha t phi of -1 plus beta t phi of 1. But turns out we can calculate phi of -1 and phi of 1 because we've chosen a particular value. But phi of 1, remember by definition, that's the integral from 0 to 1 of tau over sigma. And it turns out, because sigma and tau, they're very concrete functions, you can actually calculate this using what's called Laplace's method. And you find that, in fact, it equals to 1 over kappa, where kappa is the constant I showed before. And the idea is, if you use Laplace's method and a Taylor expansion, you get this h double prime coming out, I think, from this part, and then the h double prime of 1 comes out from the other part, and if you combine them, you do get kappa. And by symmetry, you get phi of -1 is -1 over kappa. And if you plug this in here, you do get alpha t of -1 over kappa plus beta t 1 over kappa. That's the first part. We found that 1 equals to those two things. That's good. It gives us sort of half of the equation. We get sort of the left-hand side. And now, let's figure out with the right-hand side. And of course, I'm sure you're dying now to integrate this by parts, which is exactly what we do here now. So, 2. For 2, if you integrate by parts, again, don't worry about boundary terms. Here, there might be some, but in practice, I'm using a cutoff function to say that stuff is 0 at -3/2 and 3/2. So if you do that, you get minus integral from -3/2 to 3/2 sigma over tau u xi, and you put the derivative on this phi xi d xi. Okay, and maybe the most exciting part of today's talk is the following. Remember that phi, again, we define this to be integral from 0 to xi of tau over sigma. So, by the fundamental theorem of calculus, phi xi is just tau over sigma. So, this whole thing becomes integral from -3/2 to 3/2 of sigma over tau u xi times, now tau over sigma d xi. And if you're wondering what gets you a PhD, it's this. Bang, 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 bang. Okay, and then you're left with minus, okay. A bit harder than that, okay, but still. Integral from -3/2 to 3/2 of u xi d xi. But that's very fundamental theorem of calculusable. So this equals to minus u of -3/2. And remember u of 3/2 comma t. Remember everything depends on time as well. And minus u of -3/2 t, which becomes, I guess here, equals to u of -3/2 t minus u of 3/2 t. And using some estimates, we can show that if epsilon goes to 0, this goes to 2 alpha, and this goes to 2 beta. And the reason is, here we have the negative domain, and on the negative side stuff goes to alpha, and on the positive side stuff goes to beta. And then all we need to do is to equate those two things here. We have this and we have this. So we get that 1 equals to 2 gives you the following. So 1 equals to 2 tells you that 1 over kappa of minus alpha t plus beta t equals to 2 alpha minus 2 beta. And well, if you multiply by kappa and multiply by -1, you get alpha t minus beta t equals to 2 kappa beta minus alpha, which gives you one part of the equation. And the question is, how can you get the other part? You could either use the fact that alpha plus beta is 1, or you can just take the kramers-smoluchowski equation and integrate by simply integrating kramers-smoluchowski epsilon and doing sort of a similar process. We actually find that alpha t plus beta t equals to 0. And then, if you take those two equations and add them and subtract them, we do get, in the end, that alpha t equals to kappa beta minus alpha, and beta t equals to kappa alpha minus beta. Ta-da! Which is precisely the reaction-diffusion system I talked about today. And we can almost go home very happy, but there's more excitement actually, because this proof is robust enough that we can generalize this, because in fact there were other proofs that were given which are also nice, but first of all they're very complicated, and although they could generalize other things, sometimes it's hard to generalize them, but this one is actually easily generalizable. So again, it depends which way you want to generalize them, but here are some very nice variations. First of all, there was nothing special of having 2 wells. You could do it with 3 wells. So let's do a triple well case. Well. So suppose instead of having wells at -1 and 1, you now have wells at -2, 0 and 2. So something like that. So it goes like 2, 0, 1, 0, 1, 0, 1. Supposed to be symmetric. But in this case, again, the kramers-smoluchowski equation is exactly the same because here we have this different function h, but we still have, you know, sigma ut is sigma over tau u xi xi, but with this function h. But the result is as follows. If we have three wells, then we have sigma u converges weakly star to alpha of delta Dirac at -2 plus beta Dirac of 0 plus gamma, I guess, Dirac of 2. So those three wells are alpha, beta, and gamma. And again, more importantly, the equation that they satisfy, where alpha t is kappa. So here's the interesting thing. In this case, the equations depend on the next door neighbors. So alpha depends, the next door neighbor is beta, so it's kappa of beta minus alpha. Beta, in this case it has two neighbors, and so what it really is alpha minus beta plus gamma minus beta, which is the same as alpha minus 2 beta plus gamma. And this really makes sense because if you want to go, let's say, from alpha to gamma, you have to pass beta. And also, if you want to go to gamma to beta, you have to pass it twice. So it's sort of beta does twice as much work. So we have this here. And gamma of t, the only neighbor is beta. So it's, again, kappa of alpha minus beta. I believe that the constant kappa is slightly different. It's with, has to do with h double prime at 1 and 0, perhaps a different constant. Actually, it might be the same. We'll see. We can do that. That's one thing. And of course, who says 3 says infinite. So we can do the same spiel with infinitely many wells. Infinitely many wells. So suppose you have something where it's at 0, I'm running out of black markers. So you have 0, 0, and then 2, and then 4, etc., etc. -2, -4, 4, -2, -4, etc., etc. Then you have, again, infinitely many wells. Each, you can label it with some function, alpha naught, alpha 1, alpha 2, alpha -1, alpha -2, etc., etc. And then you get basically the same result, that sigma u goes weakly star to the sum from -infinity to infinity of alpha m Dirac of 2m. And surprisingly, the equations are very similar to here. Namely, what is the equation for alpha m? Like, what's the equation of well m? It's kappa. Again, the only neighbors of alpha m are alpha m plus 1 and alpha m minus 1. So it becomes alpha m minus 1 minus 2 alpha m plus alpha m plus 1. In other words, the only interactions are with the nearest neighbors. All the other neighbors, they don't matter, interestingly. And it's, again, a generalization of this example. And I think the main miracle of this is that we can also generalize this for higher dimensions. So far I did a one-dimensional example, but we can also do it for higher dimensions. So let me do that. Okay, so here, higher dimensions. So, what I mean by higher dimensions is, so far we assume that xi is one-dimensional, but you can also assume that xi is two-dimensional, even m-dimensional. So suppose H now has two L's. So it looks like this, but higher dimensional analog. Suppose it looks like this saddle thingy. Okay. And this is the point, of course, 0, dot, 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 0. This is the point, -1, 0, dot, 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 0. Let's call this E minus. And let's call this E plus. That's 1, 0, dot, 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 0. Then you can generalize the kramers-smoluchowski equation. So kramers-smoluchowski equation becomes the following. You still have sigma ut. You still have sigma over tau. Before we had, just u xi, but now we just want to have all the derivatives. So put all the gradients. So u xi1 dot 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 u xi m. And then we have this derivative of xi with this derivative of xi outside before, but look, on the left-hand side we want a scalar. On the right-hand side we have a vector. Well, to turn the vector into a scalar, we have to take the divergence, which here is the following. The divergence of a vector is just the sum of the components, and for each component you do the xi-ith derivative. So this is a generalization of the kramers-smoluchowski equation, and surprisingly we get the same result. We get that. So here's our result. Namely, again, if you take sigma u, you normalize u with sigma, then it weakly converges to alpha Dirac at E minus at the first well plus beta times Dirac of E plus. And the cool thing is, you might think that the equations are way too complicated because it's higher dimensional. Turns out the reaction-diffusion system is exactly the same. Alpha t is kappa beta minus alpha, and beta t is kappa alpha minus beta. It's just that the definition of kappa is a little bit more complicated. Kappa becomes the following. Again, remember before we had h double prime at 1 and h double prime at 0? The analog is now the following. If you take the second derivative matrix at E plus, and again, d squared of h is, h of xi1, xi1, h of xi1, xi-m, h of xi-m, xi1, and h of xi-m, xi-m. So take all the derivatives, second derivatives, put them in a table. You get what's called the Hessian. If you evaluate this at E plus, you get a matrix. And with that matrix, take the determinant. So determinant of d squared h of E plus. Well, turns out this determinant, I think it's negative, so just do the absolute value. No, actually it's positive, but it's fine. But for the other one, it's very important. So that's like h double prime at 1. Now we want h double prime at 0. But same spiel, you take the Hessian, you take the determinant, and now it might be negative, so take the absolute value. And then here, you do an extra term, which has to rely with a very complicated estimate, but you divide by 2 pi, And then now look, this thing is a saddle point. And mathematically, a saddle point means the Hessian has positive and negative eigenvalues. And in our model, we assume there's just one negative eigenvalue. Take that one. So lambda 1 is absolute value, where lambda 1 is the negative eigenvalue of d squared h of 0. So the cool thing is we have the same equations, except our kappa is slightly different. It's still h double prime of 1 over h double prime of 0, but we have this thing. So, and somehow this thing and this thing, they cancel out in the one dimension to just get a regular square root. And finally, the interesting thing is the method of proof is almost the same, except remember before we defined our test function phi using the antiderivative of tau over sigma. Now, unfortunately, we cannot quite do that because we're dealing with several variables, but what saves us is PDEs. I guess what saves us are the PDEs. Namely, this time we define phi via the following PDE. Namely, in this case, we take minus divergence of sigma over tau, gradient of phi equals to some scalar. That scalar equals to, again, complicated definition, but the indicator function of b plus over the size of b plus minus the indicator function of b minus over the volume of b minus, where b plus minus are the regions you get when h is less than or equal to 1/4. So remember, h has this double wall potential function. Well, if you look at the point where it's less than 1/4, you have those two balls, or not balls, but two regions here, which we call b minus and b plus. And indicator functions are functions which are 1 or 0. And once you have this PDE, it turns out then you can integrate by parts, and if you use that, you do get the same result as before. So a little bit more complicated, but the idea is still, it's the same idea as before, which again makes this function very great. All right, so if you like this, congratulations for surviving the 100th video special. But if you want more goodies, more PDE stuff, please make sure to subscribe to my channel. Thank you very much, and thank you so much for all your support. I appreciate it.